This is question number 21 from the 3.2 and 3.4 MyLab Math homework assignment on derivative rules for exponential functions and log functions and the chain rule. So we're given an equation that has a natural log in it. And we can approach the derivative two ways. First of all, we can just work with the equation as it's written and take the derivative from there. And the second way is to rewrite this equation using a log rule from algebra before we start the calculus. And I'll show you both ways in this video. So let's actually start by using algebra to rewrite the equation before we start the calculus. Okay, so we have a log rule from algebra that says if you're taking an log log or a natural log of an argument that has an exponent, you can drop the exponent in front of the log. So this is not calculus, this is algebra. So I'm keeping my y equals notation. I'm just rewriting this equation and I'm dropping that 3/2 in front of the log. So now my argument is just a quartic binomial. There's no exponent attached to it. Now I'm going to use my log rule. So just as a reminder, the natural log rule says this. Okay, so here we are, our natural log rule. It says if your equation is written in the form of the natural log of some argument, where that argument is a function, okay, then the derivative y prime sends the argument to the denominator. So we have 1 over that argument, and then we tack on the derivative of the argument. So I'm going to apply this rule to find the derivative. Okay, so here we go. So my argument in this case, argument is this binomial. So I'm going to take my derivative, so y prime. This 3/2, so if I came back over here to this rule, if there's a constant in front of that natural log, that constant ends up in the numerator because there's technically an understood 1 in front of that natural log to begin with, and we end up with a 1 in that numerator, right? So just following suit, if there was a constant in front of that natural log, that constant's going to end up in the numerator. So we have a constant, it's 3/2, right? So that's just going to end up in the numerator, or you can just say it goes along for the ride. It doesn't have to go in the numerator. So just to show that in our rule over here, where that constant could just be pulled out to the front. So let me erase that there, it's being weird. Okay, so that constant could just be pulled out to the front because technically if you pull it out, if you just goes, along for the ride, it's technically over a 1. So when you multiply the numerator, it's just going to go to the numerator. So since our constant happens to be a fraction, I'm just going to pull it out to the front, like leave it along for the ride. So my rule said, okay, so that constant is along for the ride. Then my derivative rule says my derivative is 1 over the argument. Then I tack on the derivative of that argument. So that's that chain rule component there. Okay, so let's go ahead and clean this up. So that's going to be 3/2 times, side by side they're multiplying, 1 over the argument. And then to find the derivative of the argument, I'm just going to use my power rule. I don't need the chain rule because my base is a plain x, so I just need my power rule. So let's go ahead and find that derivative. So the derivative of x to the 4th would be 4x cubed. Technically times the derivative of the base, but the base is a plain x, so that derivative would be 1. And then I have a constant, and the derivative of a constant 2 would just be 0, so we don't have to write that. Okay, now we can clean this up a little bit. I'll put the 4x cubed over 1, and we can just go across and do numerator times numerator, and then denominator times denominator. We're not really multiplying it per se. I'm just going, well, I guess we can multiply the numerators because they're all monomials. So let's see what we get when we do that. So 3 times 1 is 3, and then 3 times 4 is 12, so I'd end up with 12x cubed. And then in the denominator, I would have a 2 times a binomial, and I don't want to distribute that 2 into the binomial, no, times 1. I don't want to distribute the 2 in there because these do reduce. So see how I have a 12 in the numerator, and that's a factor because it's being multiplied with the x cubed. And then I have a 2 in the denominator, which is also a factor. So the 12 is being multiplied to the x cubed, the 2 is being multiplied to the binomial, so those factors are free to divide out. So that'll simplify. So we're going to end up getting that y prime is going to be 12 divided by 2 is 6, so that'd be 6x cubed over my quartic binomial down there. Okay, so that's my derivative. That was using method 1. So again, method 1, I used a log rule from algebra to rewrite the equation, and then I applied the calculus. Okay, but what if I didn't know that log rule? What if I wanted to work with the equation as is? So that's what method 2 is. Okay, and this is going to be a little messy, and there's going to be a lot of algebra, but we can still do it. So in this log rule, my argument would be all of this, right? The binomial to the 3/2 power. That's my argument. Okay, and then we would just go into that rule. Remember our rule over here. If your equation is in the form y equals the natural log of some argument, then the derivative is 1 over that argument times the derivative of the argument, right? Okay, so here we go. So I'm going to go straight into taking the derivative. So the derivative would be 1 over that argument times the derivative of that argument. So here's my argument, and we are going to take the derivative of that. Okay, so let's go ahead and take the derivative of that argument. So let me rewrite this. I have 1 over my argument. Okay, now we're going to take the derivative of this argument. When I look at this argument, I have a base raised to a constant exponent. So that tells me that we need to do the power rule to take the derivative of that. And it's going to be the power rule with the chain rule. Chain rule is required because that base is not a plain x, it's a quartic binomial. So we have to do our chain rule there. Okay, so let's go ahead and do that. I'm going to drop the exponent down to the front. So that would give me a 3/2. I rewrite the base exactly as it's given. I decrease that exponent by 1. So I would have 3/2 minus 1. I could rewrite that 1 as 2 over 2 if I wanted to. So that would end up giving me an exponent of 1/2. And then I have to tack on the derivative of the base. So this basically had a chain rule within a chain rule. So it was a little more complicated than if you could just recognize the algebra to rewrite the equation from the beginning, but it's still totally doable. So just to recap before I go any further, what did I do here? I worked with the equation as is. So I just applied my ln rule. The ln rule says you do 1 over the argument, okay, times the derivative of the argument. But the argument itself required the chain rule. So I used chain rule to find the derivative of the log, and now I'm having to use chain rule to find the derivative of the argument, and that's okay. Chain rule within a chain rule. Okay, so let's go ahead and keep going here. So I have 1 over the argument. Okay. So, sorry, there's a lag here on my app. I'm not quite sure. Okay, then I had the 3/2, and then I had the base to the 1/2. Now I have to tack on the derivative of the base, which we did before earlier. So that's just going to be 4x cubed. So now the calculus is done. So now I just have to clean this up. And when I do, it's going to be equivalent to that derivative we got before. So again, we're just going to multiply numerators times numerators, denominators times denominators. So again, I'm just going to put any quote unquote like whole number part over a fraction. So let's just get everything here in my numerator. So my numerator, I'm going to have a 1 times a 3 times this binomial times a 4x cubed. So when I multiply the 1 times 3 times the 4, that gives me that 12x cubed again. I'm just changing the order of the multiplication since it doesn't matter. And then I'm going to put the binomial at the end of that numerator. Okay, and then in the denominator, I have the binomial times a 2 times a 1 times a 1. Again, order doesn't matter, so I'm going to put the 2 times 1 is 2. I'm going to put the 2 first, and then I'm going to rewrite my binomial okay, at the end of the denominator. And then I'm going to simplify. So just like before, we're going to simplify the 12 divided by 2. That'll give us our 6. Okay, so that 6 will be in the numerator. I'll have an x cubed in the numerator. And then we just need to do some algebra here to simplify these binomials. It's the same base, the same binomial base. So I'm going to use my quotient rule for exponents, which says you keep the base. So I'm going to keep that binomial. And then you subtract the exponent. So I'm going to have a 1/2 exponent minus a 3/2 exponent. Okay, so when I do that, that's going to give me my binomial to the negative 1 power. 1/2 times minus 3/2 is negative 1. So it's the binomial to the negative 1 power. And that negative 1 exponent tells me I can just relocate the base. And when I relocate the base, it's going to move to the denominator. Now, I could also have left it, like this. I could have entered this in my math lab. So hold on real quick. I could have just entered this. I could have written the binomial to the negative 1 power and typed that in my math lab, and it would totally have counted it correct. But I was trying to show you that it's going to match this other form that we got. So all I'm doing now is just relocating that base to the denominator to create that positive exponent. So that's what I'm going to do now. So when I relocate that, I'm going to get x to the 4th plus 2 to the positive 1 exponent. And again, of course, we don't write that positive 1 exponent because it could look like a prime, like a derivative. So when after I relocate that, then it looks exactly like method 1's answer. Okay, so again, I don't care which way you do it. If you know the log rule from algebra, it saves you a little bit of time as far as like simplifying your answer at the end. But if you don't know that algebra rule, you can just do method 2 and work with the derivative as is. It just happens to have a chain rule within a chain rule.